Hello, thank you for taking the time to learn about architecture-driven embedded software development. I'm very happy to have Thomas Schütz from Protos as our guest today. As you can see, I'm not in the office. I'm somewhere between Mars and somewhere else. I will enjoy listening to Thomas as well, as you also will do. Just one short remark. If you want to learn more from Thomas in detail, we'll have the architecture training in October, which you can find also on our website, but it will be in German and in Germany in Regensburg. And for everybody abroad, we are happy to share some of the high quality know-how and content with Thomas. And I'm very happy to welcome him as a guest, as the special architecture specialist with many, many years of experience. Thank you, Thomas, for joining us today.
Thank you, Annette. Happy to be here and to talk about architecture. So, topic today is architecture-driven development for embedded systems with real-time object-oriented modeling, a method I want to explain briefly and demonstrate in this webinar. So, the question is, why do we place the architecture development into the center of development for embedded systems, or in general? So the biggest problem we have is mastering software complexity. Complexity is the only problem we have to solve. If it's not complex, it's not a problem. If you have a safety problem and it's not complex, it's not a problem. So it's trivial to solve a safety problem if it's not complex. But if you're driving with 200 on a highway, on a German highway, and suddenly something doesn't work with your motor, with your brakes or something like that, you cannot just reboot the software system because you will have an accident. So that's really complex because it's a dynamic safety. So it's not trivial to solve because it's complex, and that's what we have to master. If it's complex, we need to cope with complexity. So, one remark about principles and about goals. Please always start with why. Probably you know the presentation of Simon Sinek, Start with Why. That's a really good presentation, by the way, at TED Talks. Always start with your goal, with your motivation. So where do you want to go? Why do you want to go there? So the blue lake here, the blue sea, that's the goal we have. But we need a little bit more. If we drive straight into to the beach now, we will fall down the cliff. So what do we need? We need principles to keep us on the road. So whatever we do, we need principles that keep us on the road, that plow the road, if you will. So let's have a look at my little pyramid of architecture principles and methods. So on top, there's always the why. So why do we want to do what we do? We need goals, we need reasons for action, we have top-level requirements. So what do we want to produce and why do we want to produce it? Then we have those principles that keep us on the road. That's abstraction. That's basically the most important principle that's behind a lot of mechanisms and methods. Separation of concerns, simplicity, modularity, and so on and so on. So you have heard of them, but usually in most projects, they're not really actively used. So everybody's talking about simplicity, separation of concerns, but if you have a look at the code or at the models, it's not there. The abstraction and the simplicity is not there because that's not something you use in your day-to-day work. So let's assume you are taking care about principles. The next level is you need to decide about methods. So what methods do you want to use? Which languages, which modeling methods do you use? Do you want to use automation? You need processes, you need to test things. There are a lot of different methods to do all this. You don't need all of them, but you need to select a few of them that really help you. And in the end, when you've decided about the methods, you need to think about tools. So what are the tools that help you with the methods, and which methods help you with the principles and keep you on the road and help you to speed up the process. So today we are mainly focusing on abstraction, the principle, automation and modeling as methods. And we're using ROOM, the language ROOM, real-time object-oriented modeling, and the tool 𝐅𝐿Trice to do that. That's what I'm going to show. So let's focus on the power of abstraction. I have a little example from a real world. So if you want to count those matches, please do that and estimate them. Yeah, most people estimate between 50 and 70 or 150 matches. And it's really hard to count very, very, very fast. So if we rearrange the matches into a pattern, and by doing that, we give the problem an abstraction level. So we sort the matches into a certain pattern that is designed to be countable. So it's the countability that's behind this pattern. And suddenly we see it's 123 matches. As you can see, this pattern is only designed to count the matches. It doesn't help you with the energy content or whatever it is. Maybe it helps a little bit because you can count them and multiply them by the energy content of a single match. But it's basically designed to count matches or to count things. So that's abstraction. So a certain abstraction always focuses on to answer a certain problem or to a certain question or certain aspect of your system. So it always reduces the information. So it's a reduction of information. So let's have a look at a bigger problem. So that's a lot of matches now. It would be really hard to count them. And to give you an analogy to software development, that's a class diagram, a UML class diagram generated directly out of the code of a medium-sized, medium, maybe big-sized motor control system for an engine control, automotive motor control system. As you can see, just to have a class diagram doesn't really help you. You see a lot of details. It's just a flat representation of your code as a diagram. Doesn't really help, doesn't really give you an abstraction. And that's what our projects look like. So we need a little bit more. We need abstraction to help with this, with our complex systems. Let's have a look at the power of abstraction and automation we get through model-driven development and tests. Let's start with what we want to deliver. We want to deliver an executable. So you want to program a machine control or a microcontroller, whatever it is. In this case, it's an STM32 hex code here. So that's really an executable. It has a lot of details about how does it the processor, the microcontroller needs to execute the program. But I don't care about the microcontroller. I want to explain what I want to do. So that's why somebody invented high-level programming languages, a lot of them actually. And in something like a C program, you can already explain how you do it. So step by step, in this case, a switch case statement, looks like a state machine, maybe state standby on, and so on. Yeah, we already have an idea of what the program might do, but still, it's explaining how you do it. What we really want to talk about is what you want to do. And that's what we can do on a model level, on a higher level abstraction, for example, on a state machine. State machine is a very nice pattern to describe on model level the event-driven behavior of a system or of a part of a system. So from executable to C program, we have an abstraction. and from the C program to the model, we have an abstraction. So we leave away a lot of stuff we are not interested in. If I want to discuss the behavior, I can discuss this on a model level much better than on C program or on hex code level of an executable on my microcontroller. So we have an abstraction here. The problem is we need to generate an executable, and that's what we had the automation for. So we can generate with the right methods and tools. We can generate from the model the C code. Then we can generate the executable. That's called a compiler. So a compiler is nothing else than a code generator. So it's basically the same thing on another level of abstraction. And that's the automation part. So if we have a tooling and a method that supports this, we can work on the high level abstraction and still get the right result on the low level here. So that's the idea. If we put the architecture in the center of development, we need a method that really allows this. With Room, we have such a method. It's I'll explain something about this later. So you can design in the architecture model the structure and the behavior of an embedded system, of a distributed real-time system, for example. That's what most embedded systems are. So you start with the architecture. Then step by step, you refine your model by designing structure and behavior, more and more structure and behavior. You dig down into your model. And then when you're done with the first iteration, you generate the application with a code generator, for example, a C code. And then you need to test. Of course, you can do unit tests, but for embedded systems, you need asynchronous tests, concurrent tests, and so on. So in that case, you can use in Room, you can use software in the loop tests. So on model level, for any component or also for your complete system, you can design and run software in the loop tests. And in the end, when you apply this to a hardware, to a ECU, to a control unit, to a microcontroller or whatever, you want to run probably a system test as a hardware in the loop test. And you also can do this with this method. And in the end, you want to automate everything with continuous integration. So whatever you do, whatever you change in your model or in your code, you want to check it in and run the compiler automatically and run the test automatically. And you can do this really good with continuous integration if you have the right methods. And then, of course, you want to iterate. And the good thing here is you can iterate on the architecture level, on the design level, on the implementation level. It's always attached to the model. You can also iterate your software in the loop, your hardware in the loop tests. It's always in the model, or at least attached to the model. So this helps you a lot. And you still can refine your architecture later in the process, which is really hard to do on a C code level, for example. The method behind this all is real-time object-oriented modeling. That's a book. We got the rights from the authors recently and from Wiley, from the publisher Wiley. Thanks to the authors and Wiley, we could bring out a new version of the Room book. It's available on Amazon and so on. So real-time object-oriented modeling has been designed for complex embedded systems. It puts the architecture into the center of the development. And it's really an architecture. It's not just a couple of diagrams like with UML. It's really the architecture, and it's formal enough to generate code. So it enables, by modeling the structure, enables the integration of many other tools and methods. So it's a very open modeling method. And the clearly defined semantics enable code generation. So it's much more specific than, for example, UML. You can use UML to model business models or business processes or whatever. With real-time object-oriented modeling, you can model distributed real-time software. That's what you call concurrent real-time software. So it's very good for concurrent asynchronous real-time systems because it's been designed to do that. For example, for telecom systems, for medical systems, for typically embedded systems, but also for bigger systems like fuel cells and so on and so on. So there are a lot of different applications. Now that's the method level. Now we need a tool to do this. We've produced an open source tool chain. It's hosted at Eclipse. It also runs on Visual Studio Code. And that's the open source tool chain 𝐼Trice, which implements basically the complete room method. So the process in 𝐼Trice is you specify scenarios, for example, with sequence diagrams. So you want to express how your components interact, or user requirements. I want to push the button and something needs to happen over there. That's a typical starting point. You can start at any other point as well. Then you define a structure of your system. So maybe the top level structure with the structure and the ports and the interfaces that are defined by ports, and the binding, so who can communicate with whom. You can refine this hierarchically, bringing in more functionality, divide and conquer by providing containment hierarchies, layering hierarchies, and so on. So that's the structural features. And then you can implement the behavior of single components by defining state machines. Yeah, you also have other methods, for example, like data flow diagrams. We've integrated data flow diagrams for closed loop controllers and so on. It's all attached to this room method, but the main method in room is state machines to implement the behavior. And then, because it's very formal, you can directly generate and run the application. So you generate C code, for example, you compile this, you flash this to your microcontroller, and that's a little demo here, 𝐼Trice on MSP430 microcontroller or an ARM or whatever it is, doesn't really matter. It's completely portable, the generated code. And then you debug on model level, for example, by generating during runtime the executed sequence diagram. And by that you debug and learn about bugs, or you can find out errors and so on, and then you iterate. And that's a really, really fast process. I'm going to demonstrate this in a minute. It's a minute or so for the complete turnaround here. So let's have a closer look at the method. The two main methods here, or the two main patterns, are components and state machines. A lot of other patterns attached, but the actors are the components in room. So it's a component-based approach. Hierarchical components called actors, they define the structure of your system. Ports are the only interfaces of an actor and define a very specific role in its environment. So you can do separation of concerns on port level, on interface level. And here you can see hierarchies. For example, the XY controller component actor has sub-actors here. So if you double-click it, you go inside and you see the XY controller has an X-axis and a Y-axis, as I expected. So, and since you need to create a tool that really works, we decided to make a complete implementation as a text-based language. So it feels more like Java than like an embedded language. So here you see the textual language, but we also have graphical editors, and they interact. So if you change something in the textual model, you can see it in the graphical model, and vice versa. But it's always persistent in the textual model for diffing, merging, versioning, branching, and so on, building libraries. That's really hard to do with some other modeling methods. So that's a very crucial thing, that everything can be done on a text-based level here. Okay, so that's the structure editor. And for the behavior, we have hierarchical state machines. Again, textual editors and graphical editors. Also hierarchies here, XY running, for example. If you go inside, you see the content of this state here. The hierarchical state machines are really good to define dynamical behavior of actors. You have a very high level abstraction for dynamic behavior, which helps you a lot to get your complexity on a behavioral level under control. So how does this all help? Let's have a look at our non-functional requirements, because the non-functional requirements drive complexity. So the functionality is very often the simplest thing in your system. So you press a button and then you open the door. But what if somebody wants to attack your door? Or what if somebody has his hand in the door or something like that? What if the motor doesn't work, if the sensor doesn't work? So those are all non-functional requirements that drive the complexity of your system: safety, security, reusability, and so on. So let's have a look at a couple of non-functional requirements. You want robustness. You want scalability, testability, portability. So all those ilities, those are all non-functional requirements. So how does this method help now? Let's make an intermediate step into the principles. We talked about principles before. So all those principles, abstraction, separation of concerns, modularity, very important, they help to fulfill non-functional requirements. And now, how does the room method help? We have in the room method, we have a lot of patterns, a lot of features integrated directly into the language, and they are all connected. And so, for example, we have those actors for the structure, we have containment hierarchies, we have layering, first-class citizen in the language. We have ports for the interfaces, state machines for the behavior. We can make a deployment, same model to different targets, distributed systems, and so on. So let's have a look at one non-functional requirement, the testability. And let's see which principles we need for testability. Usually, separation of concerns is a really good thing to help with testability, encapsulation as well. And especially modularity for bigger systems, that's what you need for testability. Not only for testability, but also for testability. And now we have a lot of features in Room that help with the different principles. For example, separation of concerns. The actors, you can encapsulate topics completely in an actor, separating them. Separation of concerns on our interface level, port level. Ports allow this, and so on. Modularity, again, actors, containment hierarchies, ports, and so on. The deployment also is a very modular concept, and so on and so on. So it's very important that your method really helps you with the principles, and the principles really help you to fulfill non-functional requirements. So an example from a project, it's a medical production plant at Paritech for inhalers, for asthma, and for colds, and so on. And that's the original drawing from the first design, paper design, from the mechanical engineer that constructed the machine, that designed the machine. And that's one of the many stations in the machine. You see all the cylinders, the gripper, the sensors, and so on. That's really original drawing. I saved this. And so what did we do? Even before they designed the machine, we already had an idea how it works. So we could already create hierarchical structured models in Room. So for example, that's a cylinder, so we use a cylinder. That's a cylinder, so we use a cylinder. The gripper is also a cylinder, and so on. And here are a lot more things internally. So there's a lot of things going on behind this conveyor belt here. So we created a hierarchical component to hide this complexity, because on that level, I just need the one part. I don't need all the processes behind it. So that's why we use hierarchies. So now I have the structure, and I have reusable components, modules, and so on. And now I need the behavior. So again, the mechanical engineer explained us what the system does and how it's supposed to do it. And we created a state machine that actually really moves out the gripper, lowers it, grips apart, pulls it up, and so on. And this is exactly what we can describe directly in a state machine and directly interact with all the components. And this machine is still working after 20 years with exactly the same machine control without any known errors. So very robust, very fast. So what else do we do with Room? The architecture model allows the integration of other tools and methods. Use cases, for example, are development of distributed real-time system. We can use it for software-in-the-loop test, hardware-in-the-loop test, integration and system test. We can run environment simulations to test or to simulate other things, to simulate mechanical systems, for example, and so on and so on. A lot of applications for Room models. And in the center of the method is always the actor, so the component. You can see the component can have a lot of different ports. That's up to you what you want to define. In this case, I have a function port to control the functionality, a control port for the life cycle of the component, for the error handling, and so on. Then another port handles the configuration. They're all completely separated. And another port handles the life cycle of the component. So whatever you need as a separated concern, the method makes sure that you can really, in the model, separate the concerns. So what you want to separate, that's up to you. It's your design. But the method can help you to really express the separation of concerns and modularity and so on in the model. So we can integrate into the actor a lot of different things, like different behavior languages, state machines, that's part of Room. It's directly integrated in the open source project. We have a closed loop control language that directly integrates also with Room, with the actor, or Protos data flow language, but you also can integrate Simulink models, for example, or generate code from Simulink models. It's not hard to do. You can also integrate high-level programming languages, C, Java, and so on. So that's to define the behavior of your components. Then you can integrate a lot of different interfaces. For example, we have a lot of generators for different bus protocols. So you take the port and you generate a CAN interface, LIN interface, XCP, whatever your interface is. Write a little code generator, and then you can generate the code and use it for production. Also, things like low-level IOs, digital, analog, SPI, I2C. You encapsulate those things into an actor, the driver, for example. You make a port, and suddenly you have an IO or a low-level bus system on a model level. So last thing, you can integrate test and verification languages. For example, the test description language and generators like 𝐾𝐽 in our mini-hill environment, our software and hardware in the loop environment. Also, we have interface contracts for model and runtime verification. So if you want to make your model not only on model level robust, but also during runtime robust, can generate, for example, runtime verification. So there are a lot of different applications. Also, you can generate documentation to understand your system better, and so on. So now, enough theory. I'm going to make a little demo. So I'm jumping into a development environment. We plugged it into an Eclipse platform here. And here you can see the application structure of my Room model. So let's start here on that level. So we have a little traffic light container. I want to program a traffic light. So let's start a little traffic light. It's just a graphical user interface with a little traffic light that has a TCP/IP port attached. It's a socket server. And it can interact with my real-time software. Could also be digital, analog IOs, CAN bus or whatever it is. In this case, it's just a little demo application. So now I want to program an application to control this traffic light. So I go inside this traffic light container, and I'm going to create the controller. So I need a traffic light controller with a state machine that controls the traffic light. So that's what I'm going to do. So it's empty, as you've seen before. Traffic light controller. I instantiate the controller in my component here. So now I need an interface that converts my traffic light commands, so turn green on and so on, into a TCP/IP command, and I need a TCP/IP socket. So I've prepared a traffic light interface. It just converts TL interface. It just converts model level language into a TCP/IP socket message. And then I need this socket. So a TCP/IP client. So let's call this socket. Those are all predefined components. That's from the library in the open source model, and that's just a little state machine that converts the messages on model level into a little text. Nothing more, just a protocol dispatcher. So now, separation of concern. I separated the control for the TCP/IP socket to configure the socket, the IP address, the port, and so on from the payload. Because, why is that? Separation of concerns. I might be forced to use another protocol in the future, and I can reuse the payload protocol, not the configuration, because UART, for example, is configured differently than a TCP/IP socket. I can use the same payload. So separation of concerns for reusability. So now I have all the infrastructure I need, and now I need to implement the controller. So let's open the controller, interface port. I give it an interface to my traffic light here. So that's the traffic light interface. So, and let's call this port TL. So I'm going back on the structural level here. I'm connecting those ports, and suddenly I can communicate. So, but now I have the complete structure. It's already, I can generate it, compile it, it already would run, but it wouldn't do anything because I need a behavior. So let's open the state machine. I'm going to create a first state to connect to my TCP/IP port. That's the port I've shown you before, connect 4441. That's the port here for TCP/IP. Now I'm going to connect it. Then the next step is I want to set initial state. I want to set, for example, the traffic light to the car should be green. The car light should be green, and the pedestrian light should be red. So that's the initial state I want to have here. And I can only do this if I'm connected. So I'm waiting at the traffic light port for the connected message. Okay. And then, as you've seen, I could also now wait for a pressed request button that's directly connected with this request button here, and so on and so on. So that's how I'm going to program the traffic light, basically the behavior, by creating a state machine. So now that's what I'm going to do. I already started the traffic light. Now I'm building and running the traffic light. That's the application I'm running now. So it's generating the code, compiling the code, running the code. And here you see the car light is green, the pedestrian light is red. I can press the request button, but it doesn't have any effect because I don't have a transition here to react on that. If I want to, it's a real-time system, so it runs endlessly. So I'm going to stop it. And to debug this, I can have a look at the log. So and here, see exactly what I did. I connected. It said to connect over the socket. It really connected. Then I sent the car green, pad red, and so on. So that's how we can debug application. We can also reduce this to only certain aspects and so on. So that's how I'm going to program my behavior here in a state machine. I'm going to cheat a little bit because I don't want to bore you with creating a big state machine now. So I'm going to deactivate this, and here I have my predefined traffic light controller. Again, I'm going to inside the traffic light controller. I'm going to lay this layout here. So, and that's basically the complete behavior of a simple traffic light. So let's have a look at that. I'm going to run this again, build and run the traffic light. Let's have a look at my traffic light. So now it's on. I press the request button and my traffic light works. It's as simple as that. So now I programmed the traffic light. I want to talk about non-functional requirements. I can reuse this traffic light now for any kind of other infrastructure. So I just need to either replace the traffic light interface here by another interface, or the socket, for example, by a UART or by a CAN bus protocol or whatever it is. I still can use the same controller logic, because the controller logic is completely abstract. It's just talking about traffic lights, red lights, green lights, and so on, not about technical details. Here, I'm talking about how do I communicate, and that's how I connect the logic with my physics. That's what the interface essentially does here. So, separation of concerns. But now I want to scale my model a little bit. So it's a little bit boring to have one traffic light if you want to control a complete, let's say a complete city with traffic lights. So stop this traffic light, and I'm going to start 20 traffic lights. So now I have 20 traffic lights. Let's assume I have to control a lot of crossings here. So now what do? I only have one traffic light controller, but it's only a class with one instance. So let's move one level up. So I could now instantiate 20 traffic lights. I could do this, but then I would need to instantiate 20 interfaces and 20 sockets. That's not why I have abstraction. I want to do this with one click. So I want no traffic light or one traffic light. So, and I move one level up, and here I have the container. So that's the container. I'm one level up, and here I can instantiate the container 20 times. So I give it the multiplicity 20. Now I have 20 times the subsystem here. So same thing, just a click. And now I want to start my, let's go back here. I'm going to start my traffic light application. And suddenly I am controlling 20 traffic lights. So they're all completely independent in this case. I could connect them with a central controller that starts up the city in the morning and shuts it down in the evening, or handles any problems or whatever it is. It's a very simple demo, but I guess it shows really good the scalability of those systems. So as you can see, and that's always robust, it always works. Yeah, because 90%, 95% of whatever I do is generated. So that's the scalability of the system. And now I'm going to show the last step. Last step is I want to make a software in the loop test, because I'm not always there to click whenever I change my application. I want to automate this test. So that's why I'm going to change this application here. Usually it's a separate application. Going to, on a text level, that's the container I just shown you. I'm going to activate the traffic light test container. So now that's a test container. Yeah? Could run them in parallel, but usually it doesn't make sense. One is manually, the other one is automated. And now the test container, I have an empty test actor here, and I'm going to drag in the component I just developed. So the traffic light controller. I just want to test the functionality of my controller. Okay, so now I have my controller, and I'm going to create a software in the loop test just for this controller. Again, that's the controller with the state machine. You remember? So now I'm going inside the test actor, and here I define a little smoke test. So that's my test case, a little smoke test. So what I want to do in this smoke test, I want to provide a couple of steps. For example, a connect step. That's the first step I want to do. I want to define an action. I want to, or a reaction. That's the first thing I do. Reaction. I want to, an action. I want to send the answer to the connect command. So that's the TL interface here. I want to send connected. So to satisfy the interface here. And the next step would be I expect check init states. I want to check as a reaction that I get the traffic light dot, no traffic light, sorry, traffic light TL interface. I want to check whether the car is really green and the pedestrian is really red. So, but now I'm going to introduce an error because, yeah, let's assume I made an error here. I ask for a false here. So now in the smoke test, I have to add the different steps, connect and check initial states. That's it. And now that's it. So now I have a software in the loop test for my component. So now that's where the test case lives. That's where my component lives. So as you can see, the test is just a reusability scenario for the same component. So I can reuse it for a test case. I could also reuse it for a completely different control system. So the tests make sure that your component is reusable and also make sure that the component works as it's supposed to. So now I am going to run the system and I'm going to start the software in the loop test cases. It's all command line, so you can completely automate this on a continuous integration server. Now I'm going to run the test, this test actor, and you see here the test was executed and it worked actually. So let's have a look at what happened in my test case. Here, that's what happened. I said I connected it. That's what I sent when my test case sent. I expected the set car red and the set car green. And actually, I made the test case correct. So let's change this to make this set car red true. Just to have a little example for a failing test case. Let's run the test case again. Now it failed. So let's have a look at the trace again. So that's the test result. The expect failed. I click on the expect and it goes directly to the right line where my reaction failed. So that's the software in the loop test. And I don't have time to show you the complete hardware in the loop test. We have different webinars also for that. If you're interested, we're making more webinars with Eclipseina as well. And now I'm going back to my slides. That was the demo. And now you can use the same method also to run hardware-in-the-loop test, signal level hardware-in-the-loop test, completely automated on your microcontroller. So that's where the models now live. We generate the environment simulations and the test cases, as you have seen. Instead of connecting them over ports in the model directly, we connect them over those wires on signal level with the pins of the microcontroller. So that's the right leg of the V model, top level integration test, system level testing. You can do it always with the same method. So the development process again is based on Rune for those test systems. Again, here you see the structure, the behavior, the test cases, everything I've shown you before, but just for hardware in the loop, not only for software in the loop. You generate, compile, flash the test system, you run it, you get the test reports also on the target, and so on. So now we have covered the complete V model. Something special, since we are working on model level, you can also generate very efficiently a lot of test cases, combinatorial test cases, robustness test cases, and so on, directly from the models. Okay, so that was it. I hope you enjoyed the webinar and the little demo. Hope to see you soon. We make a lot of different webinars also with Eclipseina. Yeah, we'll be happy to see you again in the webinar. Thank you, Annette, for the chance to present this to your audience. And back to you, Annette.
Thank you, Thomas. And I think it was very, very interesting to see. What I want to emphasize is also I've been working with Thomas since many, many years, also while I was still leading a software development department within Schaeffler. And I can highly recommend these kind of approaches because we proved even these many years ago that this method approach, whichever way you're using it, it doesn't have to be the mini hill, is a very powerful approach to have consistency between the architecture and your actual applications. And there's a reason why we've been continuing to work together over all these years in different constellations. I really would like to encourage you to have a look at the approach and to think about whatever context you're working in, how to keep the architecture and what you're generating consistent, because these architecture-driven development approaches are very, very powerful and enable you to work with a smaller workforce and to focus really on the customer needs, customer requirements, your implementation, and not the small copy and paste reworking stuff. And this is why I'm really happy to have Thomas here. And I'm really happy that we will continue a series of different events, which will focus more or less in a similar direction, but will give you different examples, different details with these webinars. The next one will be end of June, so quite soon. And then we'll have a next one in July. And after that, of course, we'll go into summer break, and in autumn, we'll be back. Thank you for joining us. Thank you very much, Thomas, for giving us these great insights. And I hope to see you again. Thank you and bye-bye.
Bye.
Can you please provide the tool chain link eTrice? Someone is asking, Thomas. Maybe you can put in the chat, yeah? Yep. Otherwise, we will upload and put some of the answers we can also put as Eclipseina, yeah?
Yeah, I'm going to post it afterwards in the chat. Yeah.
Thank you. Bye-bye.